Hey everyone! Welcome back to my Procedural Ruins tutorial series for SideEffects' Project GROT. In the previous lesson, we've explored how we can easily add targeted edge wear using our mask attribute and the lab's edge damage node. In this lesson, I will go over my favorite part of this project, making procedural flesh. The core idea is that we isolate areas fit for flesh to grow on, scatter a bunch of points, connect them, and then add a little bit of code to make them adhere to the nearest surfaces. Let's get into Houdini. Alright, here we are. We have our nice and detailed ruins model, and now we want to make flesh grow on this. But how can we isolate this area where we want flesh to grow on? Well, you might have guessed it already. We can simply reuse our mask attribute. We can do what we've done earlier, where we get an attribute transfer and plug our mesh in here. And I'm gonna get what we had in the beginning. We can maybe get one sample and then get an attribute blur. The reason why I'm using a blur is because the attribute transfer, if I increase the sample count, it's gonna diminish these areas here that are a bit thinner. And what I would like instead is I want to keep this deep red here, and instead I'm gonna use the blur because I have a bit more fine-tuned controls over how the blur is happening. So what I could do, for instance, is I can decrease the step size, that way it's less aggressive, and then I can increase the blurring iterations, and that way I still have not this aggressive step happening, but I won't lose these high values in these thin parts. And that way we have already isolated where we want our flesh to grow. And like in the first lesson, I can just get a scatter node and start scattering some points. And I'm gonna choose density scale again, and I'm gonna type mask. And I'm gonna crank up the density a little bit. Yeah, something like this. Because these points are gonna be basically the starting points of where our flesh is gonna grow. Because I primarily want the flesh to grow in the red parts and not so much in these cooler parts, I'm also gonna remove any point with a mask value lower than, let's see, I don't know, maybe 0.5 or something. Let's see, I'm gonna get a blast node and switch it to points, and I'm gonna type add mask smaller than 0.6. Yeah, I think this should be a good base for our flesh. And now what I would like is I would like all these different points to start connecting at random with each other. And there's a really handy node that does exactly that, and it's called connect adjacent pieces. And we can just select that. In the standard behavior, it's not gonna work. And what we could do is, for instance, we could choose adjacent points. But why I don't want to use this one is because it chooses the first available point to connect to. But this is a cool thing that you could use probably for a lot of other different visual effects or tools. But what I would like, for instance, is to have control over how far the points have to look before they can connect, to get some more interesting variation. And also maybe I would like the points to be able to reach over to the other side, to give this feeling of an interconnected organism that is growing over everything. So how can we do that? Well, we can do that in the original setting that we had, but to make it work, we first have to do something else. You can see if you go on the node info that it's expecting a name attribute. So what we can do, for instance, is we can get an enumerate node. And let's set that to points. So what you can see, what it's going to do is that for each point, it's going to write a value. So yeah, you know, point 0 has value 0, point 1, 1, 2, 2, and so forth. So basically, each of these points is going to get a unique value. And that's exactly what we want for the connect adjacent pieces node, because the way that it works is that if two points have two unique values, they're allowed to connect. But if both points would have the same value, then they couldn't connect. So this works just fine. Basically that's what I want. I want each point to have a unique value so that they're all allowed to connect with everything. So now we just need to call it name. All right, so we call it name. So now you can see it over here. And one thing to be aware of is that very often when nodes are expecting a name attribute, that also means that it should be a string. So that's just something to be aware of for all kinds of nodes in the future. So if we go back to our connect.json pieces node, we can see that now it did something, but it's still kind of behaving like the previous version where it just connected to the closest available point. But now we have a lot of controls available to us to change that. So for instance, with the search radius, if we increase that, we can force it to keep looking for other desirable points. And we can also increase the amount of points that it's allowed to look for, and that way it can keep looking. However, it seems as though all the points have already found a partner. What we can do though is we can change the conditions which defines a desirable connection. So for instance, the minimum distance here allows us to get rid of all these tiny pieces here. If we say, for instance, you have to look at least half a meter. So now we have something that is much more, I don't know, it almost looks like cobwebs or something, right? It goes all over the place. And yeah, and we can dial back and forth and see what feels right. So maybe 0.25. And if you're having a hard time imagining what this is going to look like later, what I like to do in those cases is I like to get a merge node just for me, get my ruins, plug them in there, and then get my connections, get them in there too. And now I can see them together. And now I can already kind of see, you know, this being something flesh-like. So yeah, so now we can play around. I don't know, I think, yeah, maybe half a meter is cool. What you can see if we rotate the camera a bit, we can see that there are a lot of these connections that are just kind of stuck inside the wall, that are really like lying flat on it, that are effectively intersecting with the geometry, and we want to avoid having those. I mean, first off, just because it doesn't look nice, and also it's going to end up being wasted geometry if we end up sweeping that and giving it thickness. So before we do that, let's remove them. So an easy way that we can detect and remove intersections is by creating a group based on the bounds of another object. And to do that, I'm first going to resample the curves we have already, because the connections that we have only have a beginning and an end point, but I want some points in the middle to have something to detect, basically. So let's get a group node now, plug that in. I'm going to set it to points. And I'm also going to call this intersections. And I'm going to plug in the mesh. And I'm going to disable the base group, enable keep in bounding regions. And I'm going to set the bounding type to a bounding object. Now we can see our ruins mesh, and we can see some highlighted points. And what I like to do now is essentially I want to now create a rule where if even just one point is intersecting, I want to remove the entire spline. And we can do that by getting a group expand node and saying get in the intersections group. I'm gonna paste the name twice here, and I'm gonna say flood fill to connected geometry. So in that way, even if just one intersects, the group fills up until the end of the spline. And so now I'm gonna get a blast node, and I'm gonna say intersections. So let's have a look. So if I enable or disable it, we can see it takes care of the worst offenders. So there's still some left here, but later I'm going to show you another trick that can get rid of those as well. These connections look pretty rad, but they still look very digital, like they're just straight point A to point B connections. But what I would like is I would like them to have a bit of more of an organic look, like, I don't know, like muscles tensing or like roots overgrowing rocks. And what we could do, for instance, is for each point on these curves, we could calculate the direction to the closest surface and then make them move towards that. So how do we do that? It requires a little bit of Vex, but it's not that crazy. We have to do a couple things. So first, what we should do is we should go back to our resample node and enable this curve view attribute toggle. If you're not familiar, the curve view attribute is an attribute that basically tells you the relative position along a curve, where the beginning has a value of 0 and the end has a value of 1. And this can be really helpful because there are many operations where you want to know roughly where you are on a curve. So for instance, a value of 0.5 would be directly in the center. And so what I would like to do with this information, for instance, is I would like to use it as a mask to drive how much these curves are allowed to move, where something that's more in the middle is allowed to move more towards the closest surface, whereas the ends are not allowed to move as much. However, a 0, 0.5, 1 kind of range is kind of tricky to deal with. So what I would like to do first, before I do that, is I would like to remap it to a range of 0, 1, 0, effectively like mirroring the curve U attribute. And we can do that with one line of Vex code. It's really handy. Let me show you. So I'm just gonna get an attribute wrangle. I'm gonna get my curves. All we have to type is at curve U equals at curve U, and then we multiply it with its own inverse. So I'm gonna get some brackets, then I'm gonna type 1 minus at curve U. If we look at our curves now, we can see that they're all blue. The highest value is lower than what we had before. But if you look closely, you can see that now we have this mirrored gradient where it starts dark blue, then it becomes light blue, and then it becomes dark blue again. And we can also look at the spreadsheet and see, so if we click here, we can see the minimum value of 0 and the maximum of 0.25. And it makes sense, right? Because as I said, the original way that the curve U would work is it starts at 0, then it's 0.5, and then 1. So if we multiply 1 with 0, it becomes 0. If we multiply 0.5 with 0.5, it becomes 0.25, and then again, if we multiply 1 with 0, it becomes 0. All we have to do now to restore the full range is to just multiply the whole thing with 4. So now we fixed it, we now have a range of 0, 1, 0, and we've effectively mirrored our curve U attribute. It's a good idea every now and then to give your nodes names when they're doing important stuff. Okay, mirror curve U. And the next step is finding out the direction to the closest surface. And if you're not familiar with Vex, this one might be a bit more advanced, but it's also not that crazy. So I'm gonna get another wrangle, and I'm gonna put these curves into my first input. I'm gonna call this get direction. And then, because I want to calculate the direction to the closest surface, I'm going to need my ruins. So let me get those as well. Here. Okay. Now I need to do 3 steps. So what I want to do is I want to write the normals onto each point. But to get the normals, I need to find out the position of the closest point. But to get the position of the closest point, I need to first find out which number this point has. Okay, so we need to kind of start in the reverse order. So let's start by getting the number of the closest point of the ruined surface. So how do we do that? So I'm gonna start by creating an integer variable called ruins pt for ruins point. What we can do is we can use the near point function. Like all functions, if you start writing the first bracket, you can see this little helper menu. What you can also do is you can Google this near point function. You can type in near point vex, and then you should find this in a more nicely presented documentation page. But what we can see is that it expects at least 2 inputs, a geometry input and a vector point input. What that means is, so the geometry input means, well, which geometry? Because if we go to a wrangle, we can see that we have several different inputs. So we just have to type in the number of the input. And I want the second one, so I'm gonna type 1 because that's, it starts at 0. And then I'm gonna type at P, because we want to use the point position to read the data. We won't really see anything happening, and that can be the scary part of programming, because you don't really know if it's worked until, well, it either has worked or it hasn't worked. So what I like to do when I'm coding in Vex and I'm not sure what's going on behind the scenes is I like to write out my variable into an attribute so I can read it in my geometry spreadsheet over here. So let's see, I'm gonna turn this into an attribute by saying I at ruins pt equals, and I'm just going to type ruins pt because that's the name of this variable. All right, let's see. And that looks good. So if I look over here on my ruins pt attribute, there's a lot of different numbers, and they're pretty high numbers, which sounds good because as you've seen in the last video, we had something around like 60,000 polygons, and I think something like 100,000 points. So that should be our ruins. If we don't want this anymore, we can use 2 slashes to comment it out, and then we don't see it anymore in our spreadsheet. So what we can do now is we can find the x, y, and z coordinates of these points. So what I need now is I need a vector because we need the position, and I'm gonna call it pt pos. And what I'm gonna do is I'm gonna use the point function, and what you can do with the point function is you can basically read all kinds of point attributes present on a geometry, and that can be on the first, second, third, or fourth input, or even something outside of our attribute wrangle. In this case, I'm gonna type again 1, and then I'm gonna type p in quotation marks because that's the formatting that it expects. And then to tell it which number, I'm gonna now type ruins pt. Don't forget the semicolons. Okay. And the last step is to now do a vector subtraction between the points of the ruins and the points of our splines. If you're not familiar, a vector subtraction is how you can get the direction between the two. All we have to do is at n, because I want to write this into the normals, equals pt pos minus at p. Okay, so we've seen something has changed, and let's disable the points and let's enable the normals. Yeah, so this is exactly what I wanted. So you can see that now every one of my curve points is now pointing towards the nearest point on the ruins surface. So what can I do now with that? Well, we can now combine all of this, the mirrored curve view attribute, the direction of the normals, and we can now move the points along this normal direction. So I'm gonna get another wrangle. We could do it all in one wrangle, but it's more digestible if we split it into 2. So now I'm gonna call this one move along normal. And what I'm going to do is I'm going to just say at p, because we want to move the position of the points, equals at p plus at n, because we want to move it along the normals. And we multiply n by, and we can now make a parameter, a float parameter, and we do that by typing chf. And I'm going to call it multiplier. So nothing's going to happen just yet because our multiplier has no value yet. We can spawn this parameter by clicking the create spare parameter button. And now we have this slider here, and if we start to drag it, we can now see that stuff is moving. And yeah, and it's doing kind of what we want. Maybe a bit janky, but it's working. Well, there's one thing where it's not working as intended, and that is these longer connections. Well, as you can see, some of these connections that are close to the surface, when they move, it looks like it's trying to connect, kind of like a root that's trying to grow along a rocky surface. The problem, however, is that these connections that go across the ruins, they don't really have anything close by. And because the near point function is literally just choosing the closest point, it ends up being kind of torn apart. Well, not torn apart, they're still connected, but effectively the points are being moved all the way. You can see that there are no points in the center, they're all just moving towards the closest point. So how can we fix that? Well, the thing is, we don't necessarily need the ruins to be the closest points. What we could do instead is we could just supply any kind of point if we want to. So for instance, what we could do is we could take some of these curves and include them in the geometry that we use to get our direction from, especially the longer ones, because the longer ones are the ones that are affected the most. So let's see. So for instance, what we could do is we could get the delete small parts node from SideFX Labs, and we can plug in our splines, and then we can set the mode to perimeter, and maybe we set the threshold to, I don't know, something like 1, or let's see. Yeah, maybe 1.5 meters is a good value. And additionally, what we can do is we can also fuse them. And what we can do that way is we break up this pattern a little bit. And now I'm gonna get a merge node, and in this I'm gonna put my ruins and these curves that I have. So now, in addition to the ruins, we have these bridges that now act as sort of a shared center for our curves. So you can see that now these different curves are trying to move towards that. But you can see that maybe I was a bit too aggressive here in the deletion, so maybe I'll keep a few more. Maybe let's do 1 meter. And if we go back, yeah, this is better. So you can see now that these various curves now have this shared center that they are trying to grow towards. And if I go back to the move along normal and I start to make them grow, you can see that now it's more like we would expect, that these longer bridges are trying to grow towards themselves, but the shorter connections, which are the ones that are more likely to be where the rock is, they're still growing towards the nearest surface. So this is already looking pretty sick. There's one thing that I noticed, and that there are some curves that manage to sneak past the intersection detection process because they manage to just perfectly grow along the flat surface. So they're neither inside nor outside, they're just on the surface. So what can we do about those? Well, what we could do in this case is try to find the cause of this. So if we go back, for instance, to the scatter node, we can see that there are points being scattered in this area. So maybe what we should do is we should try to just not let them be spawned in the first place, right? What can we do about that? Because unfortunately, that's where our mask attribute is. So I feel like it's overshooting tremendously in this area. Well, that's the problem. The mask attribute, it works really well to give us a general area. But the thing is, later on, we also want to allow the artist to dynamically add or remove pieces as they see fit. So it might be that if they only remove a few of these pieces, we have a large area that spawns flesh where it's not supposed to be. So for instance, what we could do is we could also calculate the crevices and then multiply it with the mask attribute. Let me show you what I mean. There's a cool node called the Labs Physical Ambient Occlusion node. Let's get that. It can calculate a ray traced physical ambient occlusion, but it can also calculate the valleys, for instance. And this is really handy for what we want. So you can see that now we have this really nice border exactly where the fracture is. But it comes with its own problems. And that is, for instance, that it's not aware of our mask attribute. So if there are two surfaces that are very close to each other, it would also count as a valley. So that's why I want to combine the two to get the best of both worlds, right? We have the art directed mask that gives us the general area, and then we have the fine grained detail detection of the physical ambient occlusion node. Let me first adjust the attribute so that the mask has a bit more contrast. Also, I want to flip it so that we have the red on the inside. So let's see. So I'm gonna push this over here. Yeah, exactly. Okay, that's good. So now we have deep red in the inside and blue on the outside. Maybe let's move this a bit like here. Yeah, that looks good. So now to avoid these areas counting as flesh growth areas, we can get an attribute wrangle, and we can say that at mask is at AO mask, the attribute that we're currently looking at, multiplied by at mask. So let's see. Yeah, exactly. Nice. So now we have the best of both worlds, essentially. Okay, so let's take another look. So the scatter node, yeah, exactly. So now it doesn't grow here anymore. We remove the ones that overshoot a little bit, and then let's see the end result again. Yeah, that's much better. And we don't have any hidden curves. Okay, good, good. All right, so back to the task at hand. So now we have our curves and they're moving and it's looking pretty cool. But yeah, but it's a bit janky, like especially here, right? It's a bit of an eyesore. So what we can do to get around that is we can just get an attribute blur node and blur the position attribute. Make sure to untick the pin border points, because on a curve every point is a border point. But you will see that as I increase the blurring iterations, they start to all kind of collapse in on themselves. And that's because they're all being blurred, and so they're not being fixed somewhere. But that's where our mirrored curve view attribute comes in that we made earlier. We can use the curve view attribute as a weight attribute. And that way, because our curve view is 0 at the start and end of each curve, they end up not getting blurred, but the centers will be. So at this point, I think this is where it becomes a bit subjective to what you like. So what I did as I was developing this is I would jump around between different nodes and see which combination of parameters and settings makes for an interesting visuals. So, you know, I'm gonna push them around and then see how they react to the blur. Maybe I'm gonna, you know, make the fuse a bit stronger, so that there's less to hold on to, and it's gonna make them move in a more aggressive way, you know, right, like this. And then with the blur together, it makes for a pretty interesting shape. Yeah, this is like, now we can see a bit more happening. It's starting to take shape. Yeah, something like that. So another cool trick that I learned in the course of this project is, let's say, for instance, I want it to be a bit messier. So what I could maybe do is I could start fusing some of these points together. So for instance, I'm gonna get a fuse node and then start fusing some of them, and that way get a bit more of a messy organic shape, especially here. This starts to look really cool. However, at the same time, it becomes very obvious that it's this regular effect that is applied the same amount everywhere. And so what I learned in the course of this project is that we don't have to apply the fuse the same amount over all of these points. We can also apply it in a more random, organic way. For instance, through an attribute noise. Because there's a radius attribute that we can use on our fuse node, we can use a noise to drive the radius in different areas. Let me show that. So I'm gonna get an attribute noise. I'm gonna plug that in here, and I'm gonna call it fuse radius. And if I visualize this, and we can now see that we have this 3D noise that is being applied to our curves. And what I can do now is I can pass on this noise to the fuse node, and anything that has a warmer color has a larger radius than the cooler colors. So if I apply this now, well, it's going to fuse everything because fuse is very sensitive. So what we could do, for instance, is we could change it from positive to min-max. And I'm going to go maybe negative 0.1 and maximum 0.1. Let's see. Oh yeah, that's much more like it. Maybe even a bit more subtle. 0.5 and minus 0.5. To see more what's going on, we can play with the offset. I'm gonna animate it, for instance. I think now you can kind of see what it does. Anything that has the noise on it is going to be more aggressively fused. That together with, for instance, another resample, and then turn on subdivision curves, that now makes for this interesting organic looking breakup effect. So you can see that all the parts that are affected will become a bit more cobweb-like. If we want to, we can do this on everything, but I think it would also be cool just to add some breakup to this pattern to only apply to certain areas. Of course, we can also affect the element size of this. If we want to make it smaller, it will be like, it will appear in smaller pockets all around it. If we make it larger, then we have certain parts that will be completely fused and other parts that won't be affected. So, you know, it's up to you to do with this what you want, but I just wanted to show it to you because I thought it was really cool. I guess the last thing that we just have to do is to give this flesh some thickness. And we can do that by using a sweep node. And don't be alarmed, the sweep node always errors out the first time. And that is because it expects a cross section. You know, if we wanted to, we could give it a heart shape or, you know, whatever kind of shape we want. But we can also use a preset. So here under surface shape, we can say round tube. Oh, and then it's gonna do this. And the reason for that is because until this point, we've been messing around with the normals in a brutal way, right? So we need to fix that first, but that's a really easy task. We can just get an orient along curve node, drop that before the sweep node, and it's fixed. And I'm gonna make the radius a bit smaller, maybe like 0.25. And the reason why I chose the sweep node is for two reasons. First, it has this nice end cap feature where we can, for instance, use the grid, and then it gives us these nice rounded ends. And the other one is it has this really handy scale ramp where we can affect the thickness in this nice visual representation. I wanted to do that because I thought it would look, you know, it would give it this nice organic look. I don't know, kind of like muscles connecting to bone or neurons, but of course I also want it to have a less of a linear look and more of a smooth ramp. So I'm gonna change it to a B-spline. Make sure to select all of them. Yeah, that's better. And because I've been talking about optimization in the last lesson, let's see, we're at 260,000 primitives. That's not bad. You know, we can try and tweak it to get a bit more of a balanced polygon. So for instance, we can maybe reduce the columns. We can also reduce the cap divisions. So yeah, that saved like 60,000 polys. Or if we want to, we can also go to the resample node and see if there's something we can do. But you know, it's just something to keep in check. Like if you're noticing you're having troubles with your poly count, I would definitely check the flesh and I would check the detailed ruins mesh. Now, just to make it look nice while we're working on it, I'm also gonna give the flesh some more fleshy color like this. Yeah, that looks pretty cool. And like I said earlier, we can always go back to any of these nodes and tweak it. So if I want to, like if I want more flesh, for instance, we can either go to the connect adjacent pieces node and increase the max search points, or we can allow each point to have more than one connection, or we could also scatter more points, like increase the density. But yeah, of course, you have to be mindful because this again will affect how many polygons you're gonna have. So I think now we probably increased it by a lot. So yeah, now we're at 1 million. But as long as we end up below 2 million, we should be fine. But yeah, just try to be mindful with anything that you do. We want to make something crazy detailed and interesting, but of course, at the end of the day, it has to run on someone's computer. So just try to find that balance. But yeah, I think at this point we have something really nice and I can't wait to get it into Unreal. So we're basically done with the geometry side of things. We have our ruins and we have our flesh, but we're not done. A big part of our work when we do procedural modeling in Houdini is not only the pure geometry. A big part of our work is actually invisible. It's hidden data that's stored in the background that makes sure that our materials are being applied where they're supposed to be. It's about the vertex colors that inform a shader in Unreal. It's about building a UI for the end user so that all these things that we have been doing by jumping back and forth between these different nodes can all be controlled in one nice, clean user interface. And this is what we're going to do in the next 3 lessons. And I think this is the most important part, actually. But don't worry, I'm going to split it up into nice bite-sized chunks. And the first thing we're going to tackle is the vertex colors that we're going to need for our shader later in Unreal. So I hope you had fun and see you in the next one. Bye bye!